So basically, I'm going to discuss some work that was carried out in collaboration with my former student, Jerome Quinton, and who's now at McGill, and also Saul Rappaport at MIT on the formation and evolution of binary millisecond pulsars. As you all know, pulsars are exotic objects that are very rich in physics. For example, we can use them to help deduce the equation of state of matter at nuclear densities. And this is a very difficult problem because it involves many body interactions with the strong force. There are other important questions that need to be addressed, some of which have been partly answered. What is the mechanism that causes pulsars to beam radio emission? Why are some of the most rapidly spinning ones found in binary systems? Are X-ray binaries their progenitors? Can the exquisite timing provided by these millisecond pulsars allow us to detect gravitational waves? And what is the big picture? How are all these subpopulations related? So I'm going to explore a few of those questions and try to answer them with a new scenario for how these objects might evolve. So looking at the issue of the equation of state, it turns out that recently we've been able to measure the masses of some of the pulsars quite precisely. And the first one, most famous one, is J1614. It has a mass very close to 2 solar masses. There are a couple of others that have been precisely measured with masses just slightly higher. And what you'll notice there is that you can see it right here, that this basically rules out the physical admissibility of some of the equations of state, in particular the quark matter, the strange quark matter equations of state. So these are known as soft equations of state. These solid curves represent models, basically the interior models. And you can see that there is a maximum mass that they can extend to, and so things like SQM1 would be ruled out by the existence of 1614, but the harder equations of state involving nucleonic forces, those are still robust at the present level. Obviously, if we could measure the radii equally as precisely, this would put enormously strong constraints on the equation of state and also on the internal structure of neutron stars. So in pulsar astronomy, we have the analog to the HR diagram, the observational diagrams. So this is the P.P diagram. And to date, there have been about 2,000 pulsars that have been discovered, and about 10% of those are millisecond pulsars. The fastest spinning millisecond pulsar was discovered by the McGill group in 2006, and that's the record still stands. 1.4 milliseconds is the spin period. And on the P.P diagram, so two quantities that are easily measured, we can deduce a lot about the nature of these pulsars if we make the assumption that the pulsars are perfect magnetic dipole radiators. And so we can estimate the characteristic age from the spin down time, so basically P divided by 2P dot. And we can also deduce what the magnetic field strength on the surface is like. And so this diagram contains that information. So the vast majority of pulsars are located here. They're rather slow rotators. The millisecond pulsars are located here, and as you can see, most of them are in binary systems. Of course, the magnetars with very high magnetic fields, very strong magnetic fields, are found in the upper right-hand corner of that diagram. So in terms of the millisecond pulsars, there's some fundamental questions that we can ask. How fast can they spin? Certainly, there are many groups, including the McGill group, that are actively searching for sub-millisecond periods. Why are their field strengths weak? Does the field get buried, in essence, by accretion? Why are they extremely old? And this relates then to stellar binary evolution, which is what I'm going to concentrate on. Did all of them form in binary systems? So approximately 2/3 of them are found in binaries. Probably most of them formed in binaries. And why do they have periods between half a day and 1,000 days with nearly circular orbits. Well, to address some of these questions, a long time ago, the recycling hypothesis was put forward. The idea here is that recycled pulsars are produced by the accretion from material that is transferred from a companion, a donor star, if you like, in a binary system during the X-ray bright phase of the evolution. So this would be then what we would call an X-ray binary. And then the accretion torques would spin up the pulsar and concomitantly weaken the magnetic field strength. So in terms of a very simplistic model, we have something that looks like this. Basically, we have a donor star, an ordinary star maybe it's a low mass star, maybe it's an intermediate mass donor, and that then belies the nature of these two types of binaries. And then we have the neutron star that is accreting mass. And sometimes these neutron stars are seen as accreting millisecond X-ray pulsars. And eventually, if mass loss stops, then the radial pulsar has a chance to turn on, and hence we have a radial pulsar in a nearly circular and usually wide orbit. So how did this type of system come to form? Well, in fact, there are many evolutionary channels, and the accretion-induced collapse channel is a very intriguing one, but that's not the one that we'll look at the moment. Here we have a little caricature of what could have happened to produce this type of system. We see time here in this column, the mass of the primary located here, and also its evolutionary state, the mass of the secondary, the orbital period of the binary, and also the orbital state, or sorry, the evolutionary state of the donor star, or what will be the donor star. So the idea is that maybe you start with a 15 solar mass primary and a 1 solar mass secondary in a 1400-day orbit. So these are really relatively wide compared to interacting binary system distances. And the 15 solar mass star grows to be an asymptotic giant, and it then engulfs the companion star. The companion star then spirals in towards the center, the core of the AGB, and at the same time, it basically expels the envelope. So this is known as common envelope evolution. According to what we have seen from hydrodynamic studies, the mass of the donor star, or what will be the donor star, is more or less unchanged during this process. So what you end up with is a 4.8 solar mass naked helium star in orbit with a 1 solar mass companion in a 5-day orbit. Subsequently, the helium star goes supernova, and ultimately you have a neutron star of 1.4 solar mass, a 1 solar mass donor star here in an orbit of about 5.7 days. Now, that particular orbital period is sufficiently wide that in order for mass transfer to ensue, this star here needs to be on the giant branch, red giant branch, when it loses mass. So after a certain amount of time goes by, a substantial amount of time if it's just a 1 solar mass donor, mass transfer ensues, and the envelope of the giant basically gets stripped away, and all that's left is the core, which contains a helium, is basically just a helium ash core that is degenerate, and that becomes the helium white dwarf. So in the end, you end up with so this naturally leads to the X-ray binary phase, and then when mass transfer stops, you end up with a binary millisecond pulsar with a 0.3 solar mass white dwarf, helium white dwarf, in a 64-day orbit. So that's one possible evolutionary. Mm-hmm.
So you assume the previous slide that the kick velocity has to be rather small, right?
Right.
If it's too large, then you get back to the third to last stage.
Right. So that will change then the outcome, if you like. So you might end up with a carbon-oxygen companion as opposed to a helium white dwarf companion. If it started off much wider and then it would circularize over time, it would probably have, based on the tidal circularization time scale, probably have enough time to circularize. Then the whole process would start, but with a much larger giant.
I'm a bit, I'm not remembering my numbers, but in the field, where multiple stellar interactions aren't going to be happening, aren't the white dwarf neutron star binaries tend to have a more massive white dwarf than these?
No, there's a lot of helium white dwarfs in these systems. So.
I'm not talking about larger clusters, right? Because there you can have lots of low mass giants interacting with compact stars in the cluster.
Right. Well,
the reason I ask is just related to Elmo's question that as you raise the mass of the companion and therefore the mass of the final white dwarf, it's easier to maintain the downward climb in response to the decay.
I think it is, but I think that the strength of the decay is very easy to outweigh a much more massive decay. Like you have to be very, very much more massive
right.
for the case to not just more or less drive the system.
So we do find in the field a lot of binary pulsars where the companions are helium white dwarfs as opposed to carbon-oxygen white dwarfs. Okay. So I just show you a quick animation from Ullman et al. On the common envelope process. And this is a recent simulation that they've done. And so this is sort of the egg beater type scenario. And the common envelope, the envelope of the more massive star basically is driven off in this process. So in terms of the neutron star in these systems, after the supernova explosion, you start off with periods, the usual periods of about 1 second or a little bit less. The pulsar then evolves along this line, and at some point mass accretion starts, and then this leads to the LMXB phase. It gets spun up, the magnetic field decreases, and eventually the pulsar settles into this region, which is the home of the millisecond pulsars. But to understand the evolutions, the sort of end states, you have to look very closely, or have to understand how the Roche lobe overflow model works. And so I'm just going to briefly go over the essential details of the model. The idea here is that you have a donor star, and either the orbit contracts or the donor star expands to fill its Roche lobe. So this is the critical equipotential that intersects the inner Lagrange point. So once this happens, matter then spills over to the other Roche lobe, the Roche lobe of the neutron star, and of course it has a very large angular momentum and cannot be captured directly. And this leads, of course, to the formation of an accretion disk. Now, one of the nice things about these types of systems is that they're constrained by Roche geometry. And that means that the orbital period is simply related to the radius of the donor star and the mass of the donor star. The orbital period is pretty insensitive to the properties of the neutron star. So what drives this mass transfer? Well, in essence, there are two different types of drivers. One is causes the orbital separation to shrink, and these are the orbital angular momentum dissipation mechanisms, such as gravitational radiation, which we know is always operative. And then there's also magnetic braking due to stellar winds, and that is a little bit more ad hoc. And then we could have the donor star actually expanding and overflowing its Roche lobe. And so this mass loss can take place when the donor is on the main sequence or a subgiant or is on the red giant branch or beyond. Now, I'm not going to go into the mathematical details of the Roche lobe overflow model, but there are a few salient points that I'd like you to take away from this. Yes?
Is the moment of inertia of either star change as well? Is that going to contribute to sort of?
So yes, it can contribute a bit, but it's not the dominant factor, and so normally is ignored. But you're right, there is that angular momentum flux to consider as well. So to understand the Roche lobe overflow model, we really need to look at how the mass transfer rate depends on the response of the donor star itself to various physical processes, such as its nuclear evolution, its thermal adjustment, and of course this sort of external factor, which is the angular momentum dissipation, and also to adjustments in the Roche lobe radius due to the mass transfer itself. So looking at RL dot over RL, there are three terms. This is the dissipation term right here, which causes the separation to decrease, and the separation is proportional to the Roche lobe, the equivalent spherical Roche lobe radius. And so you can see that that is always negative. This term here accounts for any angular momentum that is taken away by mass that is streamed out of the binary system. So that's what we call systemic mass loss. That always carries away angular momentum. And then there's the internal redistribution of angular momentum. And this term here can be positive or negative, and can certainly dominate the other two terms, as the case may be. So those are the three terms that in essence determine how the Roche lobe responds to mass loss and the angular momentum loss mechanisms. Then there is the radius of the star, which we assume while mass transfer is occurring, that the radius of the star is roughly equal to the Roche lobe radius. And the radius of the star will change depending on the adiabatic response of the star to mass loss, the thermal adjustment of the star because it's lost mass, and also its nuclear evolution. So when you combine all of these things together, you come up with a formula that looks something like this. So you can understand how the mass transfer rate depends on these various factors and hence timescales. Now, some of the problems are located in, or the difficult parts to understand, or at least to come up with a physical model for, are located in the denominator. So the denominator contains things like Q, the mass ratio. That's really important to determining whether this denominator is positive or negative. And also beta. Beta is an unknown factor. It accounts for the non-conservative nature of the mass transfer. So if beta is 1, it means that the neutron star accretes all of the mass that the donor sends its way, that spills into the other Roche lobe. So that would be completely conservative mass transfer. However, beta could be 0. So maybe all of the mass gets expelled from the binary system. So that is a big question mark that nobody has really addressed properly. Generally, assumptions are made, and we can learn a lot by looking at related systems like algols and things like that, and to see what values of beta make sense. Some people have tried to estimate the amount of non-conservative mass transfer by looking for shocks and things like that around these types of binary stars. But really, this is unknown. In what I'm going to present, which is really our work on this subject, we have a highly constrained value of beta. Okay, so if D is positive, then everything is fine. But if D goes to 0 or becomes negative, then the binary becomes dynamically unstable, and it enters a common envelope phase or a merger phase. In other words, just to give you an example, what could happen is that as mass is transferred, the orbit could shrink, but the donor star's radius could expand. Obviously, that leads to more mass transfer, and it's a runaway process. So that's what I mean by dynamical instability.
There are also instabilities if you don't assume that the donor star is locked from or that there's a locking between?
Right. So in the Roche lobe model, yes, they are locked, and this could be an issue for very wide binary systems. Okay. So let's take a look at the evolution of one of these systems. This is some old work that I've done, and basically we're starting here with a 1.5 solar mass donor, and you're looking at its mass as time goes by, and it starts with a whole bunch of different orbital periods. So these are the orbital periods at the onset of mass transfer. And so MC here is the core mass of helium at the onset of mass transfer, and so this is a highly evolved star compared to this, and that's why it's a giant when it comes into contact. It has a much larger radius, and therefore Roche lobe radius, and therefore separation, and therefore period. So this is an evolved star. This is much less evolved. But what we find, of course, is that there is this bifurcation limit in the behaviors of the evolution. And the bifurcation limit is basically determined by a competition in timescales between the nuclear timescale of the donor star and the mass loss timescale. So that if you can strip mass off faster than it can evolve, you won't form, for example, a helium white dwarf or a helium degenerate core in the center. And so that's the essential physics behind this idea of a bifurcation limit. Below the bifurcation limit, say for a central hydrogen content at the onset of mass transfer of 30%, we see that we have something that looks like a cataclysmic variable evolution. The mass basically just continuously decreases, the orbital period is decreasing, and this line would basically extend almost down to zero. So this is what we have, and in between, very close to the bifurcation, this is where we can form ultra-compact systems. So here, the central hydrogen content is 0.1. Again, mass transfer wins. The Chandrasekhar-Schoenberg limit is not reached, and consequently, this helium degenerate core is not formed. But because basically the donor becomes extremely helium-rich, sometimes the amount of hydrogen in these donors could be 1 part in a million, and they're fully mixed, they're fully convective. And the more helium that there is in these stars, the lower the orbital period at the minimum period. Eventually, the period, I should have mentioned this for this track as well, the period does reach a minimum and starts to go back up. And so the same would be true here. And the reason that, of course, the period is so small is that these objects are not really degenerate, and so it's just ideal gas pressure support that's holding them up. But of course, you have helium as opposed to hydrogen, so naturally you're going to have a much smaller radius. You're going to need to be more compact. And you can get down to periods of 5 minutes for these ultra-compact binaries. Now, here is a simulation that we created for one of these evolutions. And what you'll notice here is a ruler. The ruler will always be centered at, or the 0 point will always mark the center of mass of this binary system. We've got a chronometer here to keep track of things, and also the period and the mass of the donor star. So this is the X-ray bright phase. 200 million years has passed already. The mass of the donor here is down to about half a solar mass. The orbit is expanding in response to the mass transfer. Then there's something known as the luminosity bump, which causes the donor to shrink a bit, and presumably the radio pulsar turns on at that point. And then subsequently mass transfer continues. Here the mass now is around 0.3 solar masses. Basically, the envelope of that giant is only a few hundredths of a solar mass of hydrogen. The rest is just the core, and it can't sustain itself as it continues to lose mass, so it collapses. But it collapses, and the little bit of hydrogen that's left sort of on the skin in the envelope of this star actually heats up, and it undergoes a thermonuclear runaway, and can actually, in some cases, fill its Roche lobe, as it's done here, and then there can be another short lived X-ray binary phase. So yeah, the chronometer's down to hundreds of years here.
Shell flash.
Pardon?
That's
Yeah.
helium shell flash.
Hydrogen shell flash. Right. And now you can see it's trying again here, but basically it's quenched at this point. So this now is the sort of final state for a binary millisecond pulsar. The orbital period here is about 25 days. The mass of this helium white dwarf is about 0.3 solar masses. And if you want to see lots of hydrogen shell flashes, here's an HR diagram showing one evolutionary track where basically here's the luminosity bump. And here's the horizontal branch. It's heading over towards the white dwarf, the degenerate sequence over here. But along the way, these hydrogen thermonuclear runaways occur, and so you can get many of these cycles before the hydrogen burning is quenched fully. Now, I'll just quickly show you the animation for the formation of ultracompacts. Oops. Sorry. So here, the time scale is much, much longer. And so we're talking about giga-years here. The mass of this star is starting off, I guess, at around 1.2 solar masses. And again, it tries to become a giant, but mass loss is sufficient that so large that indeed it can't really develop a degenerate helium core. And at this point, the period continues to decrease, and at some point we'll go through the ultracompact phase. So it continuously loses mass. Now it's down to about 0.2 solar masses, and then most of the hydrogen gets stripped off, and what's left is more or less pure helium. And this is one of the ultracompact X-ray binaries that has been detected. So this would be a model for one of those, or say for if this was a white dwarf, then an AM Kanban type system.
So basically, when the masses have whittled down, say 0.3, the nuclear evolution timescale of the companion remains modest because of the helium, high helium content.
Right. So a lot has been done in terms of precision measurements of binary pulsars since I first started looking at this problem more than 10 years ago. And what I found based on these different types of model calculations is a relationship between the orbital period that you end up with in these binary millisecond pulsar systems and the mass of the white dwarf, the mass of the companion. So at that time, we had relatively limited precision information. The highest quality observations came from systems that had measured Shapiro delay. But what did we learn, or what did we know at that time? Well, first of all, we knew that there was this very strong relationship between orbital period and the mass of the companion, and that's really related to the fact that the core mass and the radius of a giant, which would be equivalent to its Roche lobe if it was losing mass, are very strongly related. And so that's basically the reason why you get this one type of relationship out of many different possible starting conditions that you could envision. And so what we see here is the spin-down age estimated for these various pulsars, the orbital period, and the mass of the white dwarf companion, the former donor star. And we're now able to basically use a stellar timer by looking at the cooling, measuring, taking photometric measurements of the donor star, the white dwarf star, and determining the cooling age of that white dwarf, because the pulsar spin-up ends at the same time that the white dwarf is born, basically. So you have synchrony there, and you can determine what the ages are. And generally, there was pretty good agreement. I would trust more the cooling times here, but generally there was pretty good agreement between the spin-down times and the cooling times. More recently, of course, a lot more precision measurements have been made for binary millisecond pulsars. And so you can see this is the mass of the companion star, the white dwarf, and its uncertainty. And also, in some cases, we have very good estimates for the mass of the neutron star. And that is one of the major points that I want to discuss in just a few minutes. So, in fact, I'll look at the mass of the neutron star right now. You can see that it's pretty well constrained by the observations to be between about 1.2 solar masses and about 2 solar masses. So that seems to be the range that for masses of neutron stars that are typically found in recycled pulsars. To determine the actual ensemble properties of low-mass X-ray binaries that are thus the progenitors of these binary millisecond pulsars, Saul Rappaport and his student and myself and others at MIT undertook a massive computing project where we took 40,000 different starting conditions for the orbital period of the binary. The mass of the neutron star was fixed at the canonical value of 1.4 solar masses, and also for the different masses of the donors. And so the initial conditions are all found in this box right here for the mass of the donor and the orbital period. And then we let these evolve, and we kept track of the probability of finding any one of these systems in a particular pixel, if you like, in this diagram. And so this is relative logarithmic probability. So red is highly probable and green not so probable. But nonetheless, this is not a population synthesis. This is simply our assumption that since sort of a default assumption, we'll assume that the grid is uniform. We'll start evolving systems in that grid. And so this is what we end up with. So what you're looking at here is the evolution of low mass and intermediate mass X-ray binaries. Down here we have the ultracompacts. This is the CV-like evolution. And up here are the giants that will form binary millisecond pulsars. So breaking that down, unpacking that a little bit, just taking a few sample tracks out of that ensemble. And again, you can see where the initial conditions come from. These are the CV-like tracks. You reach a minimum period around 70 or 80 minutes, and mass loss continues. These are the ultra-compact systems that could get down to periods of 5 minutes. And then there are two types of sort of giant evolutions above the bifurcation. In one case, the endpoints here where mass loss stops and you're left with a spun-up neutron star, this is for the helium white dwarfs. And in this case here, we have the carbon-oxygen white dwarfs. So that sort of breaks things down. And this was largely motivated when we did this at the time by the discovery of 1614, which had this mass for the neutron star that was well measured of about 2 solar masses. And so these are some of the tracks that we're looking at that could form that particular system. So it is a carbon-oxygen companion and has a mass around 0.5 solar masses. So taking that massive grid, we looked at the endpoints of all the evolutions, at least the endpoints that produced binary millisecond pulsars. And so the cyan here corresponds to red giant donors, mauve to subgiants, and green and red to main sequence donors at the time that mass transfer commenced. And you can see that there is a line along here. This is the famous period mass relationship where most of the helium white dwarf companions are found. And PSR J1614 is located at this is located at this point right here. Okay, so what we didn't look at was the effects of irradiation. So the feedback, if you like, from X-rays that are produced by the accretion onto or nearby the surface of the neutron star. And that's what we worked on most recently, and we're just about to submit the paper for this. So the idea is that in the accretion phase, copious amounts of X-rays are produced near the surface of the neutron star. These X-rays then feed back to the donor, and then they naturally cause the donor to expand in radius, and this enhances mass transfer. So So the question is, how does this affect the evolution? That was the basic question that we tried to address. So this is the irradiation flux that we calculated. So basically we took a point source flux, and the one parameter that we don't know is the efficiency for the X-ray radiation, because the disk could be flared, there's a corona that could scatter or absorb X-rays. There are a number of other factors, anisotropic radiation of those X-ray photons, many things like that. It is thought that maybe the efficiency factor is 10%, but frankly, it's not widely known. Now, it will turn out that our results are almost completely insensitive to the efficiency that's assumed.
So what are the typical optical depths for Thomson scattering?
I'm going to get to that in just a second. And here it is. So this is a Monte Carlo analysis that we carried out for X-ray photons, hard photons, soft photons that would apply to an accreting neutron star. So we used Tuchman's and Yehol's model for that. And the color bar here denotes relative logarithmic probability. And you can see, again, this is the X-ray energy, that in some cases for the low energy, the rather soft X-rays, that the penetration is not very deep at all. So we're looking at maybe 10 to the 4th centimeters, so just 100 kilometers below the photosphere. It's not very significant. And consequently, when we do these calculations, we're using MESA, we have to have very fine zones in the outer layers, because we have to deposit that energy in those shells and do this realistically. So we actually do the Monte Carlo simulations on the fly as we're evolving these binaries. And
Is this penetration into the companion star or into the...
Sorry, into the companion star.
Not the disk?
No, not the disk. Sorry, this is an irradiation of the donor star itself.
Are there any issues with the radiation driving outflow and that not being accounted for?
Right. So you could have radiation-driven winds, right? That's what you're thinking about. And indeed, that is part of what is built into ADA, our efficiency factor. That's the parameter we don't know. Okay, but in some cases, and this is what Philip Posiolowski discovered, the penetrations can be quite substantial, 10 to the 7th, 10 to the 8th centimeters below the photosphere. And the effect on the star's radius, so these are various fluxes that a main sequence star is exposed to. This sort of matches his results from 1991. And we see that the effects tend to be larger for stars that are fully convective, and the thinner the convective envelope becomes, so when you get down to, say, 1 or 1.5 solar masses, the less of an increase we see in the radius. But in fact, it's much more complicated than that. And that's why we had to do the full-blown Monte Carlo penetration simulations combined with the stellar evolution. So this is a good guide to the fact that there is sort of a critical flux, and that's what you should take away from this diagram, that causes the radius of the donor star to puff up a bit. Again, one has to do the calculations to know what the effects truly are.
How does the energy of a single photon compare to the binding energy of a particle on the surface of the host particle to the system? Like, can one bind a particle with just a single photon?
So you're talking about penetration of an X-ray into the donor star.
So you suppose you have a particle on the surface of the star.
Right.
It gets hit by this high energy photon.
Right.
Why would it stay in the system?
Right. So that is certainly true, and then that would be equivalent to decreasing the value of eta, this efficiency factor that we're talking about. Okay. So we're combining all those effects into this one parameter. So what you'll notice here is cycles, basically, self-induced mass transfer cycles. The green line here corresponds to eta equal to 0, which means basically no irradiation. And this is the mass transfer rate.
So we see a high mass transfer rate here. This is the luminosity bump where mass transfer temporarily ceases, and then the Roche lobe is refilled on the nuclear time scale of the donor, and eventually mass transfer stops at this point, and you end up with a binary millisecond pulsar. So now if we include irradiation, we see these massive spikes, very high m dots, exceeding the Eddington limit of the neutron star. So what we have done is to assume that that mass is lost with the specific angular momentum of the neutron star, and we allow the neutron star to accrete at the Eddington rate. So obviously the value of beta varies enormously depending on the nature of each one of these spikes and the duration of each one of these spikes. So eventually the self-induced cycles damp out, and you can see that overall the evolution between the irradiated donor star and the non-irradiated star is very similar, and that's an important point to take away. But there are important implications for this. Now, I'm not going to go into the details of this toy model that we sort of worked on, one zone model, but basically to understand what's going on, we can look at various stages of the irradiation cycle. So in the low state, before the spike, we start to have some positive feedback, and here's the radius, the photospheric radius of the donor star. This is the Roche lobe radius, and so mass is being lost, and that mass loss, which is given by this equation, depends rather sensitively on this difference between the Roche lobe radius and the photospheric radius. As this separation increases, m dot increases. This is the specific energy deposition term, and so it's basically the flux times 4 pi r squared, and so this is proportional to m dot. So this term here is proportional to m dot. So and by the way, I should say this is the conservation of energy equation. So the change in heat in terms of the energy that's deposited, the flux that leaves, and the flux that enters this one zone model from the base. And what happens is, as m dot increases, the star increases its radius. And this is what we call the high state. So now m dot is very, very large. And it turns out that once you pass the critical flux, R doesn't increase very much subsequent to that. There's a reason for that, and I won't go into the details, but it relates to the fact that the gravothermal specific heat goes to infinity as the layer becomes more and more radiative in terms of its pressure support, as opposed to the ideal gas equation of state. So ultimately you get to this high state, but what ends the high state? In other words, why does the spike, why is it the mass transfer rate attenuated? It's because of this equation right here, and the Roche lobe, whether it moves in or out, basically depends on the mass ratio between the donor star and the neutron star. So this term here could be less than or greater than 0, depending on the mass ratio. Eventually, as the system, if it survives a merger, eventually M2 is becoming smaller and smaller relative to the mass of the neutron star, and therefore the Roche lobe is going to be moving outwards. And when the Roche lobe moves outwards, you get back to this situation right here, and that's what explains these irradiation spikes.
What's HP normal? Is it the scale height of the Roche lobe?
Sorry?
What's HP in the second equation on the left? Is it the scale?
Yeah, it's the scale height at the photosphere. So here's one of the evolutions. The black curve shows how the radius changes. So this is each one of the spikes. There's sort of a modest increase in the radius and high mass transfer rates. and then subsequently, well, you can see it right here because this is the mass of the donor on this axis. You can see that the mass is constant here, so there are actually periods where there's just no mass transfer. Here, it's more muted, so well, you can sort of see the steps here, but at some point it becomes, there's always some amount of mass transfer. But the evolution really doesn't change that much from the long-term secular average, except that the mass of the neutron star is not increasing nearly as much. And now we have introduced a duty cycle. In other words, for what fraction of the time is this system X-ray bright? And in this particular case, it's about 2%. And that's going to turn out to be important, and I'll leave that to the conclusions. So I've tried to convince you that really not much changes. This is an ensemble picture of the plot that you saw previously. And this is no irradiation, this is irradiated. The general behavior of the ensemble is very, very similar. So what about the new endpoints for binary millisecond pulsars? Did they change? Well, this is what we had from, so these are observations, and these are limits here. On the lowest possible value for the mass of the white dwarf companion. No irradiation. These are the endpoints that we calculate from this grid. Now let's add irradiation. So at the 10% level, really there's not a lot of change. And moreover, this important period mass relationship that we know is correct is maintained. And this is at 100% efficiency. So there's not a lot of change, at least in terms of the orbital period and the mass of the white dwarfs. So this just shows sort of all of our different runs that we did. And the pulsar measurements denoted in green are the ones that we trust. And so you can see them right along here. And so this would be a carbon-oxygen white dwarf, which would have a higher mass. And these here are helium white dwarfs.
Sorry, what are the brown points?
These here?
Yeah.
Yeah, these are just much less precise or minimally constrained observations of binary millisecond pulsars.
But these are all
They're all
identified systems.
Yeah, that's correct.
But what's uncertain about them?
Well, we don't know the inclination angle, and so typically, we only have a mass function.
Okay. Just point, a lot more points on this plot than the previous plot.
Yeah, it's.
That's what was confusing.
This is updated. That's to the most recent data set.
This is probably been a lot of probably cluster sources, so we have a lot.
No, these are all. Sorry, I should have said these are all field sources. Yeah.
Do you, if you were happy with your prior about the distribution of initial conditions, you could compare the distribution of these things to what you get with random orientations, right?
Right. Yeah. And maybe we'll look at that more carefully. But what changes because of the non-conservative nature of the mass transfer is the mass of the neutron star. So we have fewer highly precise measurements of the masses of the neutron stars, but here are some of the observational results. This is for no irradiation. And now if we include irradiation at just 5% efficiency, we see something quite different. And this is 10% and 100%. So again, I think you can see that the masses of the neutron stars are greatly attenuated in these binary millisecond pulsars, and that they certainly agree much better with the observations. Now, if we take the natal mass of the neutron star to be 1.2, because that's one thing that we did not adjust, it was always 1.4, then we have no problem, even at 10% efficiency, to get this result right here.
Remind me, that efficiency was what fraction of the radiation was striking the surface of the companion?
Right, exactly. Right, so yeah, that's one way to look at it, but it also includes other uncertainties as well. We did a detailed geometric model as to what angles the photons were deposited at, so I didn't go into those technical details, but okay, so the bottom line is that, I mean, we do have this sort of spiky type behavior, but generally, if we're looking here at orbital period versus the mass of the donor star, so the black line here is for no irradiation. This is just 10% efficiency. And you can see that they match up fairly closely. But of course, the big difference is in the mass of the neutron star. And in this particular example, the mass of the neutron star increased by about 0.4 solar masses. You can say, well, is that sufficient to spin up these neutron stars to very short orbital periods? And the answer, of course, is it easily can do that. So there's no serious implications with respect to pulsar periods. So in conclusion then, I think that we have a relatively unified picture as to how wide binary millisecond pulsars form. And we're confident that X-ray binaries are indeed the progenitors of those systems. And the missing link that was found maybe 10 years ago or more was the accreting millisecond X-ray pulsars. X-ray irradiation feedback is a very promising mechanism to explain the properties of BMSPs, and especially the observed mass distribution of neutron stars. The predicted properties, ensemble properties, are rather insensitive to the value of eta. We tried values of eta of 1%, and we still get desirable results. So that's really important, because if our results depended on tuning this value of eta, then I would be very concerned about the robustness of the conclusions. The long-term average properties of the X-ray binary progenitors are very similar, except for the mass of the neutron star, and of course the sacred orbital period mass relationship is maintained. But I didn't really have time to go into this, but there's the issue of duty cycles and when you actually detect these X-ray bright systems. And in looking, we didn't do a population synthesis. Population syntheses, as Katie will tell you, are very, very difficult. These are what I call higher order population syntheses. Maybe CV syntheses are first order, and we can get a fairly good handle on synthesizing cataclysmic variables. But when you have to introduce kicks and various more channels and maybe an extra phase of common envelope evolution, it really increases the uncertainty. And that's part of the reason why we did not proceed with a population synthesis. We just said, let us start with this grid that's reasonable and see what it yields. And so that was the raison d'etre for taking that strategy. So the duty cycles for our models range between 0.1% and 5%. So that means that in 0.1% case, for every year that the source is X-ray bright, there are 999 years where it is not, and therefore would not be observed. And so X-ray irradiation feedback is a natural solution to the long-standing problem of 100-fold overabundance of low mass and intermediate mass X-ray binaries. And these come from the population synthesis calculations of the Northwestern group, amongst others. So I'm sure if you were to put this into a population synthesis code with these types of duty cycles, obviously it depends on the initial conditions as to what the actual duty cycle will be, that it would very easily solve this problem. I'm confident of that.
Do you expect any ultra-luminous?
Pardon?
Do you expect any ultra-luminous binaries? That depends on how the mass is actually transferred.
Right. Yeah, we've looked into that briefly, and these models do work. But of course, we were using intermediate mass black holes, so 1,000 or 10,000 solar masses, something like that. So we could make those types of models work, but I'm just not sure about the sort of intermediate range because these models don't apply to that. we're not really getting ultra-luminous systems from this particular grid set. And then, of course, there are implications for redbacks and black widow systems and transitional millisecond pulsars. And these are things that we're presently trying to follow up on. OK, thanks.
So are there any questions? So I have a question. So since you mentioned redbacks and black widows, so what I'm curious is the effect of radiation on buffing up the companion. Because right, if there's no radiation, it doesn't buff up. If there's too much radiation, then you're in this state, right? You're in redback, you don't accrete anything, you just blow off all the material.
Right.
But if there's enough, but if there's just a little bit, then you say it actually increases the mass accretion rate, right? So it seems like if we were to plot
Right.
the mass accretion rate as a function of radiation, we get something very non-monotonous.
Mm-hmm.
So where do you think the watershed is? What's the critical illumination rate when you transition from one case to the other?
So how would you like me to quantify that precisely?
So like in terms of like the Eddington emission, fraction of an Eddington, for example?
Right. So, I'm thinking somewhere around 10%, something like that.
10%. This is like regardless of the mass of the companion. This is just dependent. Just to get a picture of how this.
It's
You can't go below a companion mass of about, what, 0.2? Or
You-
your sequence?
for our sequences.
Yes.
We can have a wide range of companion masses.
Okay, in the whiteboard case, yes.
Yeah.
But it's the white generators which are undergoing these oscillations. They were, you can really get the compacts undergoing these oscillations as well.
What we were looking at are stars that are, so during these oscillations that you're seeing mostly, they're giants, really, right? And
Right,
so,
can the giant, so do the ultra compacts go through a giant phase too?
yeah, a little bit, yeah. It's, I wouldn't call it, well, subgiant phase, if you want to call it that. Sorry, you're
In those tracks, you get these big spikes as well.
yeah. Mm-hmm.
Okay.
So, to Alok's question, isn't there some regulation? Because if you exceed the Eddington limit, the accretion efficiency goes down in terms of photon output. And so, doesn't that saturate the irradiation of the companion, and therefore prevent you from going way beyond the accretion, way beyond the Eddington?
You don't need much feedback in order to get the effect. So, one would have to do the calculation. It's really quite complicated, the different types of scenarios that can occur in these outer layers, depending on the thermal profile, the thermal structure of the donor star, its chemical structure, the mechanism for transport of energy. There's not a one-size-fits-all. So.
And the ram pressure of this excess mass loss isn't important.
We're looking into that, and so we're doing some SPH calculations right now where we're trying to investigate that effect.
It's expanded sample of the low mass binary pulsars. Which radio surveys discovered? They exploded under its binary most.
Right. No, it's been.
Steady accumulation.
Yeah, steady accumulation over time. So a lot is Arecibo surveys, I would say.
If there aren't any more questions, let's take the speaker again.